We've seen that the Laplace transform is pretty handy for working with differential equations, so we should come up with as many tricks for calculating the Laplace transform as we can. Now, the definition of the Laplace transform, which is right here, is pretty clumsy to do explicit calculations with, so we'd like to avoid using this definition whenever possible. And we've seen that we can come up with some rules for calculating Laplace transforms that come from this definition, but once we've figured out the rules, we can just use the rules without having to do explicit calculations involving this tricky indefinite integral. So just like when you first took calculus, one of the big projects for your first calculus course is coming up with a derivative rule for every situation. We'll come up with as many Laplace transform rules as we can so that we can just use those rules instead of doing explicit calculations with this clumsy definition. We have a few Laplace transform rules, like we know the Laplace transform of powers, well, positive integer powers of t. We know the Laplace transform of the exponentials that look like this. But there are a few other situations that are good to have rules for, and here's one. So the Laplace transform of a function times an exponential. This is sort of common in applications where you have some sort of influence that decays over time. So f of t would sort of be playing the role of the influence, and the decay over time is reflected by e to the at. You'd have some sort of exponential decay here. So let's figure out what this Laplace transform is. Of course, the first time you work out a Laplace transform rule, you have to use the definition because there's just no other way. So let's see what happens. So integral from 0 to infinity of e to the minus st times, so our function goes in here, so that's e to the at f of t dt. So one of these exponentials is coming from the definition of the Laplace transform, and the other one is coming from the function we're taking the transform of. Of course, now that we have both of those exponentials sitting there, we should probably put them together. That seems like a good idea. So integral from 0 to infinity of e to the, let's see, it's going to be minus s minus a times t, so careful with the minus signs. It's kind of nice to have that minus out front, so that's why I did it that way, times f of t dt. So it's a little tricky to know exactly what to do with this expression, but if we make a little substitution, it should make it a little more clear. So let's introduce a new variable. Let's call it u, and u is going to be s minus a. Now, since the variable s is not the variable involved in is not the variable for the integral, right? That's t. S acts like a constant for this integral. We can just replace s minus a with u, and there's no other adjustment we need to do to this integral. So this is integral from 0 to infinity of e to the minus ut f of t dt. But this expression should look familiar. This is just the Laplace transform of f, but the variable, instead of being s, it's u. So I've been using this notation where the Laplace transform of f is script L applied to f. If you use the notation where the Laplace transform of f is just, you denote it capital F, then this would look like capital F of u, like this. But, right, we need to get back to our variable s, so undo our substitution. We get the Laplace transform of f of s minus a, or if you're using the capital F notation, this would be capital F of s minus a. So what we found, right, this is the Laplace transform of e to the at times f of t. What we found is that an exponential multiplying by an exponential over in the t world, in the s world, it looks like a shift in S by A. Now you have to remember that there's a minus in here and not a positive, so maybe you might want to say this is a shift to the right. But the general sort of slogan version of this Laplace transform rule is that an multiplication by an exponential in t gives you a shift in S. So an exponential in t gives you a shift in S. And so we can use this Laplace transform rule to work out some examples.